Imagine three identical metal spheres resting on a ledge. We release them at the exact same moment, but with different initial conditions. The first drops. The second is thrown straight down. The third is launched straight up. Regardless of their direction, all three spheres share two universal parameters. They start at the same height, h, and are subject to the same gravitational acceleration, g. This setup gives us three distinct physical cases: an object dropped from rust, an object thrown downwards, and an object thrown upwards. Calculating their flight times or final velocities doesn't require three different sets of physical laws. By establishing a single, strict reference frame, one set of universal equations will naturally adapt to predict the outcome of any initial motion. These three equations govern all constant acceleration motion. They link initial and final velocity, acceleration, displacement, and time. To make these work across different trajectories, we must define a frame of reference. For this analysis, we define downwards as the positive direction. Since gravity pulls toward the Earth, gravitational acceleration, our variable g, is directed down. In our reference frame, g will always be a positive variable. Rigorous adherence to this sign convention is the only way to model different trajectories without creating mathematical errors. We start with case 4, the simplest scenario where the sphere is simply dropped. This diagram establishes our initial variables. Because the object is dropped, the initial velocity, u, is 0, acceleration is g, and total displacement, s, is the height h. Looking at the derivation for final velocity, inserting 0 for u simplifies the equation to v equals the square root of 2gh. For the time of flight, rearranging the displacement equation gives us t equals the square root of 2h over g. This zero initial velocity scenario serves as the mathematical baseline for our analysis. In case 3, the object is thrown downwards. The updated diagram shows a downward arrow for the initial velocity, u. Because the throw is downward, matching our positive reference frame, u is a positive non-zero number. Looking at the equations on the left, the time equation now includes the ut term, resulting in h equals ut plus 1/2 gt squared. The updated final velocity equation becomes v squared equals u squared plus 2gh. The addition of that initial velocity term mathematically ensures a higher impact velocity and a shorter flight time than our baseline drop. Finally, we analyze case 2, launching the sphere vertically upwards. This diagram shows the object traveling up, reaching a peak, and then falling past the starting ledge to the ground. Here, the object's motion opposes our downward reference frame. Therefore, we must plug in the initial velocity as a negative value, negative u. Despite the upward path, the total displacement, h, remains positive because the final impact position is below the starting ledge. Inputting these conditions into the displacement equation gives us h equals negative ut plus 1/2 gt squared. Because we now have a negative term tied to time, we can no longer isolate t through simple linear rearrangement. This forces us into a more complex mathematical approach. To find the flight time, we first rearrange the displacement equation into standard quadratic form. We multiply by 2 to clear the fraction, arriving at gt squared minus 2ut minus 2h equals 0. Next, we substitute these specific variables into the quadratic formula. We then methodically step through the algebraic simplification of the radical. This yields our final result for time. T equals u over g multiplied by the quantity of 1 plus the square root of 1 plus 2gh over u squared. We discard the negative root of the solution because time must be a positive value. The physical complexity of a direction reversal mid-air is perfectly captured by the mathematical necessity of a quadratic equation. Beyond time of flight, we can analyze the final impact velocities of the thrown objects. Look at the impact velocity equations side by side. On the left is case 2, thrown up. On the right is case 3, thrown down. Despite case 2 traveling a much longer path, the equations for impact velocity are identical. This is because the initial velocity term is squared. Squaring the negative velocity of the upward throw results in the same positive value as the downward throw. While the direction of the throw determines the path and time, it does not change the final kinetic energy upon impact. The first takeaway is that an object's physical path dictates its time of flight, requiring a quadratic solution whenever the direction of motion reverses. The second is that final velocity is strictly a function of starting height and the absolute speed of the throw, regardless of whether that initial motion was up or down. Ultimately, we don't need different physics for different trajectories. One equation, bound by a strict frame of reference, is universally capable of defining the entire system.